Cool. Welcome in, everyone. Another great day here at Atlanta Metro. So last class we were talking about the kinematic equations, talking about displacement, changing your position. Talked a little bit about vectors, scalars, coordinate systems, time, velocity, and speed. Talked about velocity, acceleration, position, how those things are related. Velocity, speed. Yeah, one big thing, we always talk about speed and velocity. One major difference is that speed has no direction. The speed is a scalar. Velocity does. Velocity has vectors. Okay, that's why this plot changes, because it actually does have a vector. So when you go backwards, the velocity may change. Position versus time may be linear. Velocity versus time will change. Alright. See, speed versus time, linear. Alright, so acceleration, the change of your velocity over the change in time. So final minus initial velocity over final minus initial time. So we learned about that last time. Deceleration and a negative acceleration, talking about the different points of our plot. Whichever way we want to show is a positive x direction or a negative x direction. Typically we do positive y going up, negative y going down, positive x going right, and negative x going left. So a lot of times we'll have our negatives that way, calculating acceleration. Hey, great day. Oh, hey, great day. How you feel? You doing all right?
Yeah.
Yeah. All right, so now looks like we're on 2.5. So motion equations for constant acceleration in one dimension. So we're gonna be calculating displacement of an object that's not accelerating, given our initial position and velocity. Calculate the final velocity of an accelerating object, given initial velocity, acceleration, and time. And calculate displacement and final position of an accelerating object, given initial position, initial velocity, time, and acceleration. So these are called kinematic equations. The dynamics, understanding the change of motion. All right, so last class we were also able to understand some of our position. Well, we went over, of course, doing some units again, but we had a cool talk about our velocity and how we changed. So that was a lot of fun doing our experiments.
Some were slower than others.
So we did a walking experiment to see how our regular walking speed is, our regular walking velocities, and talked a little bit about acceleration. So that was real cool. So that was a great way to get closer to chapter 3. Alright, in this section we developed some convenient equations for kinematic relationships, starting from the definitions of displacement, velocity, and acceleration, already covered. So we'll be using T, X, V, A, time, position, velocity, acceleration. Let's make some simplifications in notation. Taking the initial time to be 0, as if time is measured with a stopwatch, it is a great simplification, since elapsed time is change of time equals final minus initial time. Taking T initial equals 0 means that the change of time equals the final time. The final time on the stopwatch. When initial time is taken to be 0, we use the subscript 0 to denote initial values of position and velocity. That is, the initial of x is the initial position, and initial of v is initial velocity. Put no subscripts on the final values. That is, t is the final time, x is the final position, v is the final velocity. This gives a simpler expression for elapsed time, which is now. The change of t equals t. Also simplifies the expression for displacement, which is now the change of x equals x minus x initial. Also, it simplifies the expression for the change in velocity, which is the change of v equals v minus the initial v. To summarize, using the simplified notation with the initial time taken to be 0. So here are some of those. In the absence of we now make the important assumption that acceleration is constant. This assumption allows us to avoid using calculus to find instantaneous acceleration. Since acceleration is constant, the average and instantaneous accelerations are equal. So average acceleration equals a, which is constant. So finally, in motions where acceleration changes drastically, such as the car decelerating to top speed and then braking to a stop, the motion can be considered in separate parts, each of which has its own constant acceleration. Solving for displacement and final position from average velocity when acceleration is constant. To get our first two new equations, we start with the definition of average velocity. So we talked about that. The change of x equals the change of time. Substituting in the simplified notation, so we're just putting in the change of x over the change in time, x minus x naught over time. Solving for x, so we also have x equals the initial x plus average velocity times time. So that's just moving, you're just isolating the variable x. So we're just, if we're giving a velocity and then we don't know its position, we don't know its final position, we can look at its initial velocity and then add the acceleration, the velocity that we have, and then multiply that by time. So that's a real cool thing. So now we're looking at initial v plus v over 2. So we'll see how this relates here in a second. The equation v equals v naught plus v over 2 reflects the fact that when acceleration is constant, v is just the simple average of the initial and final velocities. For example, if you steadily increase your velocity, that is with constant acceleration from 30 to 60 kilometers per hour, then your average velocity during this steady increase is 45 kilometers per hour. Using this equation to check this, we see that this happens. So that makes sense, which seems logical. Yep. Calculating displacement. How far does the jogger run? So a jogger runs down a straight stretch of road with an average velocity of 4 meters per second for 2 minutes. What is this final position, taking his initial position to be 0? So of course, always start out drawing a sketch. So we talked about that. Try to have a free body diagram. So if I start out with my initial position and then I know my velocity, I'm trying to understand what my final position is.
So what's the initial? The initial is
It's just gonna be 0. So they told us take the initial position to be 0.
The velocity is
4
Okay.
Mhm. And then for 2 minutes, so we have a time too.
Okay, no time.
So we have our x, initial, the velocity,
Time.
and then the time. Find x, we identify the values, da da da. Identify the knowns. So here's the exact strategy that we've been talking about, a free body diagram, the knowns and unknowns, and then the equation. See? Identify the knowns. We just talked about that. Enter the known values in the equation, and we get something pretty simple.
Now that part where, you know, you have the 4 meters per second, and the final is 480 meters.
Mm-hmm. Yeah, so our initial position 0, and then we're just adding the average velocity times the time.
Oh, okay, never mind.
So we only have to do velocity times time. So and then we have a meters per seconds and a seconds. Or they gave us 2 minutes. So if, of course, if we have 2 minutes, we got to change that to seconds, 120 seconds.
Okay, yeah, I see.
So now we have our seconds to cancel out, and we're left with meters. So that's a good indication that we're in a good response for our position. Velocity and final displacement are both positive, which means they are in the same direction. Very good. So this equation gives insight into the relationship between displacement, average velocity, and time. It shows, for example, that displacement is a linear function of average velocity. By linear function, we mean that displacement depends on v rather than on v raised to some other power, such as v squared. When graphed, linear functions look like straight lines with a constant slope. On a car trip, for example, we will get twice as far in a given time if we average 90 km per hour than if we average 45 km per hour. Yep. So that makes sense. Constant linear relationship. Solving for final velocity, we can derive another useful equation by manipulating the definition of acceleration. Acceleration is the change in velocity over the change in time. So we know the change in velocity, final minus initial again, and then take our time, final time minus initial time. But when we have our initial time being 0, then we just have to use our final time. So that makes it a lot easier if we're doing like a stopwatch type of situation, as opposed to 2 seconds. It's already 2 seconds in, and then I look at the change from 2 seconds to 4 seconds. So something to think about. So solving for v says v equals initial velocity plus acceleration times time. So that looks very similar, huh? Looks very similar to our position. So all these kinematic equations, they look very similar because, you know, it's position, velocity, acceleration, and they're all just built on each other. The change in position over time is velocity. The change in velocity over time is acceleration. So it's an easy way to think about it. Calculating final velocity. An airplane slowing down after landing. An airplane lands with an initial velocity of 70 meters per second and then decelerates at 1.5 meters per second squared for 40 seconds. So decelerate, acceleration. So that's our indication that it's a acceleration aspect, and it's meters per second squared this time, because it's the change in velocity, which is meters per seconds over time. So we have to divide by time again, so it's meters per second squared. So just a few little highlights.
Position, right?
Our position is going to be it does not matter at the moment. Yeah, because it's just looking at our final velocity. Yeah, so it doesn't, I don't think we need it at the moment. Which we would, if we wanted to derive position, we could look at, 70 meters per second. So, and then we're gonna look at, how many seconds? 40 seconds. So, and then we could still say it took 70 meters. So we would know, it took 70 meters to go each second, and then it's 40 seconds. So we could still say what that position is like that, but not necessary at the moment. Identify the knowns. Initial velocity, 70 meters per second. Acceleration. So since they said decelerate, that's our indication to use negative 1.5 meters per second squared. And then our time of 40 seconds. Identify the unknown. In this case, it is final velocity. So what are they asking for? An airplane lands with an initial velocity and then decelerates.
After landing.
Yeah, what is its final velocity? Right. Determine which equation to use. We can calculate the final velocity using the equation v equals v naught plus at. Plug in the known values and solve. So very similar here. So my final velocity equals the initial velocity plus acceleration times time. Typically, you don't have to remember this exact equation. Typically, it'll be given. So 70 meters per second, we have a plus at, but since it's deceleration, we'll use a negative because acceleration is a vector as well. So if it's decelerating, we need to denote that it's negative. So negative 1.5 meters per second squared times 40 seconds. We cross out seconds here. We're left with 1 on the bottom. And then this is meters per second plus meters per second. So we're able to have 70 and then just minus, plus what we get up here, negative 1.5 times 40. So we're left with 10 meters per second. All right, the final velocity is much less than the initial velocity as desired when slowing down, but still positive. With jet engines, reverse thrust could be maintained long enough to stop the plane and start moving it backwards. That would be indicated by a negative final velocity, which is not the case here. Hey, welcome in. How's everything going?
All right.
Good, good. So that's what this looks like. So, imagine a runway and the plane's coming in 70 meters per second. So it's always good to know it, this is the same thing going on here. So they just simplify it. It looks easy. It looks better this way. If you actually draw the free body diagram, draw the little plane, it really helps with your knowledge. All right, 70 meters per second. Some deceleration is telling us our initial time. What is our final velocity they were asking for? So, and then we're able to do A times T. So we have, and our initial. So this is what it'll look like. So they have those arrows to help you realize, there is deceleration. Well, now after we land, it's going to be a slower velocity, which makes sense in real life, as you would know. In addition to being useful in problem solving, the equation v equals v naught plus at gives us insight into the relationships among velocity, acceleration, and time. From it, we can see, for example, that final velocity depends on how large the acceleration is and how long it lasts. If the acceleration is 0, then the final velocity equals the initial velocity, as expected, because velocity is constant. if acceleration is 0, then the final velocity equals the initial velocity. When you don't have friction, by the way. Once friction comes in a little later, then we'll have to take friction into account. But if I'm driving in my car and I just let it coast, you know, let the what's that when you let it coast? No, when you turn your car on
Cruise control?
Cruise control. Yeah, what's that thing called? So when you put it on cruise control, it's like just keeping your velocity the same. So my initial velocity, that's a way you can think of constant. It's constant. It's just on cruise control. All right. If A is negative, then the final velocity is less than the initial velocity. All right. So just like we said, experiences to check that they do indeed describe nature accurately, you know, in light of our intuition. So, railroad connection, the space shuttle Endeavour blasts off Kennedy Space Center in February 2010. The intercontinental ballistics missile has a larger average acceleration than the space shuttle and achieves a greater velocity in the first minute or two of flight. But the space shuttle obtains a greater final velocity so that it can orbit the Earth rather than come back directly. The space shuttle does this by accelerating for a longer time. Solving for final position when velocity is not constant. So we can combine the equations above to find a third equation that allows us to calculate the final position and constant acceleration when we're experiencing constant acceleration. So, of course, we had that velocity equals the initial velocity plus a times t. So we're solving for final position. All right, so we want to get final position. So if we add initial velocity to each side and divide them by 2, so v equals v naught plus at. So and then looking for, if I just put in v, that'd be v naught plus initial v. So initial v plus, because I moved it to the other side. Okay, so they just want us to divide by 2, add initial v to both sides. So initial v plus the v, and then divide by 2 equals the initial v plus 1/2 at. So this is about to give us our next one, position. For a constant acceleration. Right, so this is the same as average acceleration. So that's what, average velocity. So that's what they're telling us. That v naught, initial v plus final v over 2 equals the average velocity. Average velocity equals initial v plus 1/2 at. Now we substitute this expression for displacement, yielding this equation. So typically something like this, where like they're dividing by 2 on both sides, you know, you typically don't have to do this type of equation, but a lot of times it'll be the last equation. The last equation is what we're looking to do. You know, these are just paths to get to that. Now we substitute this expression for average v into the equation for displacement. X equals initial x plus average velocity times t, which we talked about earlier. So then if we plug that in to understand the average acceleration is v naught plus v over 2. So and then we're going to have x equals initial position plus initial velocity times t plus 1/2 at squared at constant acceleration. Alright, so we'll see how this comes
Can
together.
you scroll back up just a
Yep.
second?
Yeah, so we'll see how this comes together when velocity is not constant. Motion equation.
Yeah.
Alright. So this is a real world application. Calculating displacement of an accelerating object, the dragsters. Dragsters can achieve average accelerations of 26 meters per second squared. Suppose such a dragster accelerates from rest at this rate of 5.56 seconds. How far does it travel in this time? How far? Looking at x, looking at position. Alright. Given acceleration. Mhm. So we have our free body diagram, my x naught, what is my final x. And then they also have a coordinate system, so they're telling you, don't forget about your coordinate system. They're just telling you, hey, my positive x is this way, my positive y is this way. I know negative x if it's deceleration is that way, negative y is that way. So just letting you know about that. We're asked to find displacement, which is x if we take the initial x to be 0. Think about it like the starting line of a race. It could be anywhere, but we call it 0 and measure all other positions relative to it. We can use the equation x equals x naught plus b naught times t plus 1/2 at squared once we identify v naught a t from the statement of the problem. Identify the knowns. Starting from rest, like we said, of course, velocity is going to be 0. A is given 26 meters per second squared. T is given 5.56 seconds. Plug the known values into the equation to solve for the unknown. So once again, it's the same strategy. Draw a sketch, free body diagram, knowns and unknowns, plug that into an equation. Solve for what we need to solve for, which is x, position, how far. All right. Since the initial position and velocity are both 0, so cancel that out, cancel the v out. This simplifies to x equals 1/2 at squared. Substituting the identified values of a and t gives 1/2 times t, 26 meters per second squared. Oh, that's a t squared, which is 5.56 seconds. And square that. So my position, I get 402 meters per second, or 402 meters, which makes sense. All we have to do, we got our second squared, so both of those go away. Second squared and second squared. We're multiplying, so we're left with meters. 1/2 26. That's like 13 times 5, 156. So makes sense. If we convert 402 meters to miles, we find that the distance covered is very close to 1/4 of a mile, standard distance for drag racing. So the answer is reasonable. This is an impressive displacement in only 5.56 seconds, but top-notch dragsters can do 1/4 mile in even less time than this. So just like they're telling us, oh, if we converted meters to miles, try to make sense of it. Oh, did we get a good answer? Does our answer make sense? So so that would probably be the next part, is draw a free body diagram, go ahead and get the knowns and unknowns, plug that into an equation. Does our answer make sense? That's pretty much the last step. What else can we learn by examining the equation? We see that displacement depends on the square of an elapsed time when acceleration is not 0. The dragster covers only 1/4 of the total distance in the first half of the elapsed time. Yeah, which makes sense. If acceleration is 0, then the initial velocity equals average velocity. And blah, blah, blah. All right. Solving for final velocity when velocity is not constant. Fourth useful equation can be obtained from another algebraic manipulation of previous equations. If we solve velocity equals the initial velocity plus at for t, we get t equals, so we're just moving this around. So we want t, so we're just isolating the variable, move this around.